So 6.2 is all about taking these scatter plots and creating what they call line of best fit. And I'll show you what that means in a minute. So you already know what a scatter plot is, right? And these scatter plots can help you determine a correlation, right? Do all the points line up in a linear fashion or not? Okay. So when we look here, this following scatter plot, right, gives you a positive correlation because there is somewhat of a line that I could draw. And if I draw a line to go close to all those points, it would have a positive slope. So we would say that this scatter plot has a positive correlation, right? Now, with it, in these scatter plots, we draw what we call a line of best fit. Okay, what line can come close to all the points, right? So if I click, here's your scatter plot. When I click the line of best fit, right, this is the line that fits that data the closest, meaning it gets as close as to every point as possible. Okay. Now with this, when we look at the study guide, you'll see that the line that mostly closely fits the points on a scatter plot is called the best fit. It is also called a regression line. And this is important to know because when we go to the calculator, that's what you'll see, right? We call it a linear regression model. Okay. Now, to sketch a line of best fit from a scatter plot, we draw a line that is close as possible to most of the data points. Okay. And this is important. So if we have a bunch of data here and we want to draw that line of best fit, I'm trying to come as close to each of those points as I can. Now to do this, the first thing we do is we select 2 points on the line. So basically you construct the line, then you choose 2 points on the line, right? These may or may not be included in the original data. Then we're going to determine, right, the slope of the line. Then we're going to write this equation in point slope form. And then we're going to basically simplify this to rewrite it in slope intercept form. Remember, an equation of a line, we have 2 forms. Point slope form is y minus y1 equals m times x minus x1. And what you have to understand is y1 and x1 come from the ordered pair. And that ordered pair would be your x1 and y1. All you're doing is taking those values and plugging it in. M is the slope of your line, which basically the slope is your change in y over your change in x. Okay, so all of this goes back to what we did earlier in the year with linear functions. So the next one says, suppose you used a graphing calculator to find the equation of a line of best fit and we're presented with the following data. Okay. When we get to the checkup, I'll show you how to actually calculate it in your calculator. But it says, suppose you use the graphing calculator to find the equation of the line of best fit, and we're presented with the following data. So right now, when your line of best fit comes in your calculator, you will see all of this written on your calculator. And what it's saying is, A technically is your slope, and B is technically your y-intercept. So in this case, the slope of the line of best fit would be the negative 3.672339, blah, blah, blah. And the y value of the y-intercept would be 0.454567. That would be your y-intercept. So we would write this, all we're doing is plugging the value of a and b into this function, and, excuse me, your linear model would be y equals negative 3.67x, and then plus 0.4546. Okay, so this would be your regression model. Now, using and analyzing these regression models, something that's very important. A regression line is used for predicting what we call unknown values, right? A lot of times, like restaurants and schools, governments will use these regression lines to predict future values, populations, prices, cost of products, right? All these different things. So the explanatory variable, all right, or also known as the independent variable, is the x value, and the response, right, or dependent variable is the y value. Now, the slope of a regression line tells you the rate of change. If it is positive, there is a positive correlation. If it is negative, there is a negative correlation. The constant term in the regression line frequently predicts a starting value, or I prefer to use initial value more. Okay? So in this example, right, the regression line modeling the number of push-ups Juan does each day is, right, y equals 0.631x plus 0.0357. Now, remember, the number of days is your independent variable, and the number of push-ups is your dependent variable. So this is basically your input. This is your output. So the explanatory variable here, right, or the independent variable, right, is days. And the response variable here would be the number of push-ups. So now, Juan increases the number of push-ups he does by about, remember, if each day you're going up, how much are you going up? Well, the slope of this, you're going to use the slope, which is 0.631. So the number of push-ups goes up about 0.631 each day, which means there is a positive correlation between time in days and the number of push-ups Juan does. All right, residuals. Anytime we talk about residuals, a residual is the difference between the actual value, right, and the predicted value. Okay, since we're not touching all of the points in the data, right, what happens is we determine how close that point is to the line using residuals. So the steps to finding a residual is substitute the points, x value, into the equation to find the predicted value of y. Then what we're going to do is subtract the predicted value of y from the points, right, actual y value. So it's the predicted, it's the actual minus the predicted. So suppose the regression line modeling ticket sales is y equals negative 5.9x plus 170.85, where x represents the ticket price and y represents attendance. So here, x is your ticket price and y represents your attendance. What is the predicted attendance when the ticket price is $5? So all we're going to do is we're going to let x equal 5. And we're going to plug that in here. Y equals negative 5.9 times 5 plus 170.85 0.85. So I go to my calculator, negative 5.9 times 5 plus 170.85. When I hit enter, I get 141.35. Okay. Now, if you think about that, why would this be negative? Well, if ticket prices go up, generally attendance goes down because people don't want to pay. That's why this might and probably does have a negative correlation. So now the actual attendance, right? So they're telling you the actual order pair is when X was $5, the ticket price was actually the attendance was actually 160. So what we're going to do is take 160, subtract 141.3, and you would get the residual is 18.7. Okay, so that's how you find the residual. Now, in a residual plot, the explanatory, or also known as the independent variable, is found on the horizontal axis. The vertical axis shows the residuals. Okay. So basically, if these residuals seem random, right, and are about evenly distributed between positive and negative, that means the model is probably reasonable, right? Now, here's the thing. If your residual is positive, that means it's above the line. If your residual equals a negative, it is below the line, right? So when we look here real quick, right? So right here in this example, find the residual. Well, what is the distance from this actual point to the predicted value? Okay, well, right away, I see I'm below the line, so that residual will be negative. Okay. Now, if you use the line of best fit, y equals 2x plus 1, to find the predicted value when x is equal to 4, right? That's going to tell me that 2 times 4 is 8, plus 1 would be y is 9. Okay. Now, what is the residual for the point 4, 8.4, right? Well, we said, when you look at it, the residual for 8.4, right? If I look 8.4 is below, it's negative. In the distance of the y value, we said the predicted was 9 and the actual was 8.4. So we know we're below, so we know it's negative. And 9 minus 8.4 is 0.6. And that would be the residual. So what is the residual for 0.3? 7.3, right? So 3, right? 7.3. I know it's above, so it's going to be positive, so it could be all of these, right? Now, the line of best fit is y equals 2x plus 1. So 2 times 3 is 6. 6 plus 1 is 7, right? So the predicted is 7. The actual is 7.3. So we know it's going to be 0.3. Okay. Now, in a residual plot, plotting residual gives you an idea of whether your model is a good one. The smaller the residuals, the better your model. But the pattern and distribution of the residuals are also important. After calculating all of the residuals, you can make a special scatter plot called a residual plot. So here is your scatter plot. Here is your residual plot. Okay? In a residual plot, the explanatory variable, or x, is found on the horizontal axis, just as your scatter plot. But the vertical axis shows the residuals rather than the response variable. So here's what we see. Okay, so this would be your residual plot. Now, when we read it, these can be positive or negative, and the x-axis may appear in the middle of the residual plot, which is what we want. The table shows the x and y values as residuals for a simple example. Now, when we look here, right, here is your line of best fit, and this is the distance away from that. So these black dots are your actual value, and the blue dots are your predicted values, right? And with this, here's your plotted residual. Now, as you can see, the residuals, these plots tell you how far from the line of best fit you are. We want as many of these dots to be closest to this line here as possible. Okay? So, here, the closer the residuals are to the x-axis, the better the line of best fit the model is. So when you have your residual data, when you plot them, the closer these dots are to that horizontal axis, the better the line of best fit. An obvious pattern in the data could mean that the function is not, right, linear. Okay, so let's look here. Use the following data to calculate and interpret the linear regression equation. Worldwide carbon dioxide emissions have increased over the years as Earth's population has grown. The table shows the world carbon dioxide emissions in millions of metric tons from 1950 to 1990. Which is the explanatory variable and which is the response? Explanatory, right? Your x values represent the year, and the response values, which are your y values, represent the emissions. Okay? Now, they want us to calculate this linear, right, regression model. What I'm going to do is take out my calculator, right, and I'm going to enter this data. So the first thing we do is we click Stat, Edit. Now, notice how I already have data plugged in here. I can go and delete these one by one, or I can hit second, then the plus sign for memory, and you'll see number 4 is clear all list. So I'll hit 4, enter, and now when I hit Stat and then Edit, I get blank list. So what I'm going to do is I'm going to enter these years. So I'm going to go 1950, enter, 1960, enter, 1970, enter, 1980, enter, and then 1990. Now some people would like 1950 be year 0 and then go up and go 10, 20, 30, 40, so on. Now, my other list, I'm going to go 6,000, 9,500, 15,000, 19,300, and then 22,500. Now, I hit enter. Now I'm going to go to get the regression model, right? I'm going to go Stat. I'm going to arrow to the right for calc, and I'm going to go down to linear regression. I'm going to hit enter. I'm going to use list 1, list 2, all the way down to calculate, and here is my regression model. It ends up being, my regression model is y equals 428x. So if I look here, my A value is 428, so that goes there. My B is negative 828,700. So I'm going to go minus 828,700. Okay? So now, if you remember yesterday with our R value, my R value is 0.99, and that's really close to 1. So this is going to tell me my data is really, really close to a best line. And I'm not asking you to do this, but if I went 1900 to 2000 here, and then I want my Y max to be, say, 30,000, and I hit graph. Uh-oh, why aren't they coming up? Window. Uh-oh. So when I graph the scatter plot here, you'll see that these dots line up in a very close linear fashion, right? So right away here, so the line of best fit for this function would be this equation here, and that's taken straight from the calculator. Again, enter your data, stat, edit calc number 4, enter, 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 and you get all your numbers here. Okay, so what does the slope mean in context, right? Basically, remember, it's the change in y over the change in x. So what this means is the emissions over a year. So basically, since our slope is positive, our emissions go up 428, right? And remember, up here it says in millions of metric tons, goes up 428 million metric tons per year. Okay? And then if I wanted to estimate the emissions in 1978, right? So if I look to find the emissions in 1978, I'm going to let X equal 1978. So when I plug that in, 428 times 1978 minus that, right away I'm going to go 428 times 1978, hit enter, minus 828, 700, hit enter, and I get 17,000, what was that, 17,884, right, million metric tons. Okay, so the next part of this, they want you to use the data in the table in regression and the regression line from question 2 to calculate and analyze the residuals. So what I did is, right here, I just wanted to show you that all I'm doing is plugging these years into our regression model, right? So I'm basically doing 428 times 1950 minus 828,700. When I do that, I get 5,900. Then when I plug 1960 into our regression model, I get 10,180. When I plug 1970 in, 14,460. Then when I plug it in here, I get 18,740. Then I would get 23,020. Right? Now, so what you have to remember now is your residual value is equal to your actual value minus your predicted value. So when I do 6,000 minus 5,900, that would give me a residual of 100. 9,500 minus 10,180 would be negative 680. Now, since this is positive 100, we know it's above the line. Negative 680 tells me that point's below the line. 15,000 minus 14,460 is 540. That's above the line. 19,300 minus 18,740 is 560. Then 22,500 minus 23,020 will give you negative 520. Okay? Now, those would be your residuals. Okay? So, when we calculate the predicted emissions for each year in the table, right? These are what we get. When we calculate the residual for each year in the table, right, this is what we get. And if we plotted the residual, remember, right, this is our x-axis, right, which means our year. So that's 1960. I'm trying to figure out how the years go here. 62, 4, 3. So if I were to plot the residuals, right, I would go 1950 is somewhere right here. So it's 100, right? So it's 1950, 100, 1960. If I go up to my chart, 1960 had a residual of negative 680. So we're going to go negative, that's 600, right about there, right? And up here, 1970, we'll say is right about here. And that had a residual of 540. 1980 had a residual of 560, so maybe a little higher. And 1990 was a little below negative 500, right about there. And is this a good, does this indicate a good linear fit? And the answer to that is yes, right? Because the points are scattered above and below the line, all right, with no obvious pattern. Okay, so with this, there's a lot of stuff going on, all right? So right here, use the points on the graph to estimate the line of best fit for the given scatter plot. So when I look here, they actually give you two nice ones, one here and one here. If they didn't, you would have to look on this line for nice points. So we're going to use the 0.38 and the 0.76. And the first thing we're going to do is find the slope. Now, I could use a graph to find the slope where I go down 1, 2, 1, 2, and over 1, 2, 3, 4. So it's negative 2 over 4. Or I could just say y, x, minus 6 over 3 minus 7, which gives me 2 over negative 4. So my slope would be negative 1/2. Now I'm going to plot this or put this in point slope form. So y minus y1 equals m times x minus x1. So I'm going to plug in, pick one of these points, and I'm going to put x here. I'm going to put my y value here. Then I'm going to put my slope here. So y minus 8 equals negative 1/2 times x minus 3. Now I'm going to go ahead and simplify this, okay? When I go to simplify this, first thing I have to do is distribute. So y minus 8 equals negative 1/2 x, then a negative times a negative is a positive, 3/2. Now, when I add 8 to both sides, I'm basically going to get negative 1/2 x. Now, this is the same as 1.5 plus 8, which is going to give me plus 9.5. Okay? So according to the line of best fit, which of the following statements is true? An average of 0.5 milliliters of liquid evaporates each hour. Are we gaining or losing? All right, since evaporate means loses, right? That means our slope would be negative 0.5. The second option is an average of 2 milliliters of liquid evaporate each hour, or the time in hours is dependent on the liquid or on the volume of liquid. Well, here's the thing. Time represents your independent variable because it's your x value, so you know that's not true. So I know I'm between these two, and if you look, our slope is negative 1/2. Therefore, it's this one here. Now, use the line of best fit to estimate the original volume of liquid. Right away, in our line of best fit, this is usually our starting value or our initial value. So I would say about 9.5 milliliters, or if I look at the graph, that would be your initial amount when you first started. So 9.5 would be the original volume of liquid. Go ahead, work on the quiz, and let me know if you have any questions.